Today, I'd like to introduce you a paper from the magazine Mutil-modal Transportation. It's called an Advanced Intermodal Service Network Model for a Practical Transition to Synchromodal Transport in the U.S. Freight System, a case study, whose first author is Nasibeh Zanjirani Farahani. I hope you can learn something. Free mode choice, termed synchromodality, is an extension of intermodal service network design and is still in the early stages of modeling development. European countries have already started moving toward realizing this innovative transportation system. However, advancement in global transport with longer distances is rare and needs more infrastructural preparation and studies to clarify the steps for such a transition. In this paper, an advanced intermodal service network model is proposed to support the development of synchromodal transportation systems. This mixed integer programming model finds the optimal path between OD pairs while considering horizontal integration of variant transport modes in a supply chain network along with resource constraints and time windows. It minimizes the total transportation cost, transshipment cost, and tardiness with a penalty for delays at intermodal terminals, and overdue costs at the destination that accounts for the opening and closing times of the terminals. In order to solve the model for large problem instances, an efficient multi-objective genetic algorithm using a novel coding approach is developed. The algorithm is tested on 2 US-based case studies, showing the capability of the model to provide cost and time-saving advantages in long-haul freight. The results of this study can be applied to long-distance global transportation with similar geography and scale. The proposed model is an extended version of the shortest path problem with a time window. In these NP-hard problems, as the size of the problem grows, the computational time increases exponentially. Therefore, exact solutions become unattainable when the network size grows. Step 1: Initialization. Initial population can be generated heuristically or randomly. Heuristic initialization has higher mean fitness and finds the solution faster than random initialization, but the solution might fall in local optimal. To construct each chromosome, the intermediate genes are selected randomly or heuristically from the nodes list created based on the connectivity matrix while prohibiting repetitive node selection in the initial population to prevent raw selection and loops. This process continues until the destination node is reached. Although feasible or infeasible routes might be obtained during the random generation, infeasible chromosomes are expected to gradually fade away through the influence of the objective function, as explained later. Figure 1 shows a schematic representation of 2 sample chromosomes. The initial population is given as a parameter to the model. In the literature, the population size of a network with 20 nodes is typically 25 to 50 chromosomes. Step 2: Evaluation. To find the best chromosomes, an objective function is defined for the model to assess the performance of each generated route. Step 3: Termination. The most frequently used termination condition is the maximum number of runs in network design problems. Gonin has suggested 30 runs for a network with 20 nodes and a minimum of 50 generations. The GA uses 2 approaches as termination rules: the early stop rule and the firm stop rule. The early stop rule checks if the objective function has not changed in several iterations in one run. The second rule compares the current objective function with the past to make sure the new run is significantly better. Step 4: Generating new population. Referring to the similar models mentioned earlier, the proposed GA chooses 5% of the best and 5% of the worst chromosomes, and randomly picks chromosomes between the best and worst chromosomes to create a new generation. Parent selection and chromosome selection for mutation are made randomly. Step 5: Crossover and mutation. After selecting some chromosomes from the generated population, a percentage of the population is selected for a crossover, and a percentage is used for the mutation. If the chromosomes have less than 5 nodes, just one node would be chosen, and no mutation would happen for chromosomes with a length of 2. An example mutation over a chromosome is shown in Figure 2. After selecting the node, they are substituted with a random node from the node list created from the connectivity matrix to make sure the selected gene is different from the current one, and the chromosome is not repeated while a feasible chromosome is generated. In this case study, a manufacturer in St. Louis plans to transfer wind farm components to Rock Creek Wind Farm 2 in Fairfax, Missouri, by potentially using any available modes of transportation. The question is, what is the optimal routing for this problem considering minimization of time cost, possible delays, and overdue penalties based on the opening and closing times of intermodal terminals shows the base map for the Missouri intermodal facilities and transportation infrastructure that was used for the definition of the network. The source and destination can be seen on this map. Figure 3 also shows, considering all possible transshipment options at intermodal terminals. In the last few years, synchromodal freight transportation was introduced to logistics providers as a real-time free mode choice approach to help them save total transportation time and costs while operating more sustainably. Although European countries have focused on the requirements to realize synchromodality for years, the U.S., as a large country with much potential to benefit from this transportation methodology, has not shown much interest. The major reason for this delay is the unclear monetary benefits of this shift for carriers and forwarders. Moreover, this change cannot happen in one step and needs planning and preparation. Instead of waiting for an ideal synchromodal network design, this paper suggests modifying the current intermodal service networks in the U.S. by adopting some concepts of synchromodality. A routing model named an Advanced Intermodal Service Network model is proposed, formulated, and analyzed to show such a possibility in practice in the current situation. This model considers the primary assumptions of synchromodal transportation, such as horizontal integration or free mode choice in each path, as an addition to the current intermodal transportations in the U.S. The model considers link capacities, time windows, and delays when minimizing the total cost of transportation, transshipment, and delays. This model either can be solved using an exact method and an innovative genetic algorithm. The proposed also may be considered for the real-time routing and scheduling of transportation planning when the freight is in the middle of the shipment. Additionally, it could motivate logistics providers in the U.S. to collaborate as an integrated network to minimize their total costs and time. The model can be extended in several ways, such as expanding the concept to dynamic networks and networks under disruption and using stochastic parameters.